Hello everyone, I'm Yao An, a postdoc from Tsinghua University. Now my presentation is about the effects of climate change on agricultural water use in China. As for the motivation, it is predicts that 66 countries with 21% of the world's population would suffer from severe water deficiency by 2050, with per capita water resources at a quarter of the world average level. China is considered to be one of the most water-scarce countries. The water endowment of China is of 2,100 cubic meters per capita annually, with almost 80% of these resources concentrated in the source. The agriculture sector accounts for more than 60% of the water use over the past decades, with its irrigation water use efficiency in China being 20% lower than developed countries. Additionally, world or China has already encountered a gradual warming trend and some devastating climate extremes. So we come up with the research questions. Briefly, our project will investigate two major research questions. First, we answer how society will be affected by global climate change through its effect on agriculture. Second, how and to what degree climate change affects agricultural water efficiency in China. As for our contributions, is as following. First, we construct a set of fine-scale meteorological factors involving linear and nonlinear shocks of temperature and rainfall. Second, we address the volatility and regional disparity impact of climate change. Third, we integrate the agricultural water demand model with an efficiency component that captures the climate change-induced efficiency volatility in a single step. Last but not least, we highlight endogeneity issues in a single-stage stochastic frontier analysis estimation. Before verifying aforementioned research questions, we divided the whole countries into 6 regions. They are North China Plain, Yangtze River Basin, Northeast, South Coast, Southwest, and Northwest. Agriculture production is dependent on at least 4 types of nature endowments. They are like, for example, water resources, precipitation, temperature, and growing degree days. Here we pick up these 4 endowments and portray its distribution. Obviously, the figure shows that the distribution of endowments across geographical locations in China, we observe significant regional heterogeneity of nature resources and meteorological conditions. South Coast, Southwest, and Northwest have relatively ample water. North China Plain and Northeast suffer from severe shortage. Here's our data and their summary statistics. With the most widely employed ones being the non-parametric data envelope analysis and the parametric stochastic frontier analysis. We follow the SFA approach based on microeconomic production theory, as SFA is superior to DEA in dealing with measurement errors and potential biases due to omitted variables. The agricultural water demand can be viewed as an input agricultural water service. We will, from the perspective of economic factors, agricultural characterizations, demographic impact, and technical aspect, to examine its demand, and we extend equation 1 to 2. The second part measures the level of agricultural water use in efficiency, which is assumed to be a one-side non-negative stochastic disturbance. Following the traditional SFA literature, in our case, the focus is on the effects of climate on the level of agricultural water efficiency. Therefore, we have to allow the level of agricultural water efficiency to change over time and rely on a vector of covariates. GDD evaluates the extent of suitability of a region for certain crop production. HDD explains the impact of extremely high temperatures on yields. For the empirical results, we find that lambda here is statistically significant, revealing that the relative contribution of the inefficiency component compared to variance in the stochastic term is substantial. Here, we see that higher temperature may show the adverse impact on agricultural productive factors. It exhibits the enhancement of nutrient circulation, evaporation in the farmland, and the fall of organic matter in the soil. Under the circumstance, it is deemed to increase the risk of water shortage for agriculture. As for the precipitation, it increased in the south and northwest, so it raised the runoff, which benefits crop yields and improves the agricultural water use efficiency. From Model 3, From Model 2, we estimate the nonlinear impacts of temperature on crop growth by separately evaluate the extent of suitability of a region for certain crop production and extremely high temperature impact on the crop growth, as well as nonlinear rainfall effects, including precipitation and its square term. To study the impact of information disclosure, we introduce the interaction term between climate variables and crop damage area. In general, CDA, which is crop damage area, reflects damage information attributed to extreme climate conditions. Interaction term is negative and statistically significant. It shows that farmers will take action to improve the water use efficiency when such information is available. The information on weather variation is difficult to precisely obtain for farmers. Therefore, they tend to overlook the precautionary and ex-ante measures to lower the potential damage from climate change. After investigating its general impacts, we turn to obtain the average agricultural water efficiency score and verify the regional disparity. We obtain the agricultural water use efficiency is about 0.55 to 0.63. As for the disparity of agricultural water use efficiency, the southwest, North China Plain, and northeast appear to have the best performance, followed by the Yangtze River Basin and the northwest region. The South Coast region performs the poorest. It has been experiencing the huge pressure on deficient water resources in recent decades and is lower than the national extreme water scale line. It is increasingly valued by authorities. Here we follow the strategy where the endogenous regressors, after considering a single-stage SFA model for a consistent estimation for the robustness check. Last but not least, we got the conclusion. First, we obtain the average national agricultural water use efficiency of 0.5 to 0.75 after considering climate change shocks and potential endogeneity issues. Second, temperature-related climate change have negative impacts on agricultural water efficiency. The decline in precipitation due to climate change lowers the agricultural water efficiency. When the information on damage is observable, the negative effects of climate change on agricultural water efficiency can be alleviated. Farmers tend to overlook the potential damages of climate change as it is relatively difficult for farmers to predict. Second, farmers take actions only when they are suffering from disaster. Last, in response to the climate change shocks, regional efficiency levels are highly correlated with natural endowment. Specifically regions affected positively by climate change tend to present the lower efficiency because there is no incentive for efficiency improvement if one region is benefiting from climate change with favorable climate conditions for crop production. Last, we conclude the policy implication as the following 3 points. First, it is necessary to promote the establishment of water markets so as to fully exert the economic leverage of water price. Second, facilitating stringent water law and management institutions, especially regions with abundant water resource. Last but not least, developing drought-resistant crops and adjusting planting cultivar based on the climate change effects. Thanks.